Students, it's Mr. Rankin, and this is your next lesson in the unit on climate and water with soil. Teaching point, please write this down in your notebook. I'll be able to observe how water can interact with subsurface soils at the water table. Now, the prefix sub means below, right? Subsurface, which means below the surface. We have our soils, and we have the water table. All right, now going back to a previous lesson, our first lesson here, please take a look at this picture, one of our first lessons. We have the saturated zone and the unsaturated zone. All right, the saturated zone here is soil. Remember, it's building up. Bedrock is somewhere down below. Water is building up. We have groundwater. So the water that I interact with every single day, if you have relatives who live in Nassau County or Suffolk County, out by me, we get our water pumped from the ground every single day. That water is treated and we're able to use it. So we have wells that are drilled in the saturated zone to withdraw water. So all the soil particles, or the sediment particles, or just the word particles in general, the pore spaces between them are completely filled with water. And in the unsaturated zone, right, the pore spaces are not completely saturated. There is some water left there as it passes through. The same way how, like when you get out of a pool or you get out of the ocean, if you're in the ocean, the same way that water would beat up on your skin or stick to your skin is the same way that water can stick onto sediments or soil particles below the surface. I mean, that's the only way vegetation can survive. The tree roots, grass roots, bushes, right? All the root systems will be getting the leftover water in the unsaturated zone. Sometimes the saturated zone can be a few hundred feet below the surface. So root systems cannot reach that far. So between these two zones, the unsaturated and saturated zones, we have a line here called the water table. The water table helps differentiate between these two zones. All right, let's take a look at the video.
Today we're going to do a cool water experiment. It's pretty cool. Cool water experiment. This experiment uses the capillary effect. The capillary effect is the movement of a liquid along the surface of a solid caused by the attraction of molecules of the liquid to the molecules of the solid. For this experiment, you need 2 glasses, colored water, and a paper towel or a tissue paper. First, take 2 glasses. Put them side by side. Now, fill one of the glasses with the colored water. Now, grab the paper towel. Pinfold it or fold it in the middle. Dip one of the ends of paper into the colored water and put the other end into the empty glass beside it.
All right, take a look. Immediately, it's absorbing.
Leave it this way for a few hours. You can observe that the colored water gets transferred into the empty glass through the paper towel. The water keeps flowing into the other glass until they attain an equal amount of water in both of them. Now let's take a closer look. Molecules of water are naturally attracted to each other and form temporary hydrogen bonds with each other. Their attraction for each other on the surface of a solid gives rise to surface tension. These molecules are also attracted in a similar way to other molecules called hydrophilic molecules, such as those in the fibers of a towel. These attractive forces can draw water upward against the force of gravity to a certain degree, which explains the transfer of water into the empty glass. This concludes the cool water experiment, and I think you'll agree that it was pretty cool.
Eventually,
Click here to subscribe to
both
our
of those
channel.
would disappear if you leave them out because of evaporation. Okay, let's get this down, please. Upward motion of water. We have capillary action. That definition is the upward movement of water through the pore spaces in soil and rock. Just like in the warm-up, we can see that the water is moving upward against gravity, defying gravity, moving upward. This is a solid, almost like subsurface soil, right? All of these grains of the tissue paper are really, really, really close together. There's really no gaps between them, no pore spaces. So it's just going to absorb that in it. And the soil below the surface does the same thing, but just above the water table. This is called, again, capillary action. If I bring it back to this picture, we have a thing called the capillary fringe, in which water can rise slightly above the water table, defying gravity, and all dependent on particle size. All right, let's check out this video. This video is showing a good example of capillarity and the spacing between sediments or soils.
Before the sequences using time-lapse photography, here is a demonstration that illustrates the principle of capillarity. This principle is involved when water moves into dry porous materials. Liquid is pulled because of the attraction of solid mineral surfaces for water, adhesion, and attraction of water molecules for each other, cohesion. Adhesive and cohesive forces are responsible for moving water upward against the downward force of gravity. In this demonstration, water rises between two closely spaced plastic plates because of the adhesive forces between plastic and water and cohesive forces between water molecules. The height of rise is greatest when the plastic...
So right now, the two plastic pieces are very far apart, right? When she's going to squeeze the pieces together, you're going to see a rise of water in between these two plastic pieces.
Plastic plates are pinched tightly together. The pressure in the water above
Upward
the free
movement.
water surface in the container is less than atmospheric pressure. This is called tension. The higher water rises, the greater the internal tension.
Or the smaller space between these two plastic sheets.
Now to the models and time-lapse pictures.
Okay. So using page 6 of your reference table, which can have the greatest capillarity? All right, so go to page 6, look at the upper right-hand graph. You have all your sediment sizes, right, from clay up to boulder. So think of an answer, pause the video, and when you're ready, unpause it and listen to the answer. Okay. So based on the video, we saw that you had the greatest rise, capillarity, when she squeezed those two plastic pieces closest together, which would reduce the amount of space between them. So we want the smallest space between grains. Since the grain sizes of clay is the smallest, that means that clay should be your answer. The least capillarity would be for boulders. The spacing is so big between them, water has a tough time almost like rock climbing up these big spaces. Easier to climb up when those spaces are smaller, like for clay. All right, let's get this down. So here is a relationship. This could be a graphing relationship. As sediment size decreases, capillary action increases. If one goes down and one goes up, that means that, that means if one goes up and one goes down, that would have to be an inverse or indirect relationship. So we have fine sand, we have sandy loam, we have silt, and we have clay. Right? I think of loams as maybe like a little mixture of different size particles. So that means that this sand is probably poorly sorted, which means you reduce the porosity, and that means that the pore spaces become smaller. So the fine sand is the biggest one of these, right? That's going to have the lowest upward movement. Here you have maybe a poorly sorted sand substance, raising up a bit more than the sand. Silt is smaller than sand, and this is silt loam, so maybe it's a mixture of different sizes too, maybe a little bit of clay in there. And that goes up even higher, and clay is the smallest sediment size, the smallest pore spaces, easier for water to climb up like a rock wall. And you have your greatest capillarity when your sediments are smaller. Indirect or inverse relationship. Next, water stuck around the grains. We have capillary water held in between soil grains. Plants can absorb it. This is the water that's in the unsaturated zone that really helps to absorb the water in its root systems. Capillary water can diminish a great deal, especially if there's drought conditions. If there's drought conditions, that means the soil becomes drier, especially at the surface and near the surface being your subsurface soils. And that's a great concern. Water retention. Retention is to retain. Retain is to hold on to. The maximum amount of water that a given soil can retain, hold on to. All right, so based on water retention, right, so which sample do you think might retain the most water as it passes through? All right, look at page 6, pause the video, and then unpause it once you have your answer. All right, so the greatest retention is where you have the particle sizes very close together. Bigger the pore spaces, water has a tough time sticking onto. In addition to being small pore spaces, water can pass through it very slowly through, which means it can hold on to and retain that water much better than larger soils. Next, we have the zone of aeration and the zone of saturation. All right, the zone of aeration, is called the unsaturated soil or rock above the water. The zone of saturation, right, is below, right? So saturation is completely filled with water. Aeration sounds like air, mostly air, mostly air, and there's a little bit of water in there that can get retained. Zone of aeration, unsaturated soil or rock above the water table. And the saturation zone, or the zone of saturation, saturated soil or rock below the water table. All right, and here's your example. We have the water table down below, right between these two zones. Same here, right? We have zone of aeration, zone of saturation. Now the aeration zone is similar to this, right? The unsaturated zone is the aeration zone. They're synonymous with each other. So these pore spaces completely fill with water. These pore spaces, mostly air. There is some water retained. All right, so why do you think it is important for a soil scientist to understand how much water can be held in the soil after infiltration has occurred? All right, so think of an answer, pause it, think of an answer, and then when you're ready, unpause. Okay, soil scientists would really want to know how much the soil can hold on to after infiltration has occurred. Now, infiltration is the downward movement of water into the earth, right? The earth absorbing that water, taking it in. Now, if we have soils in which water infiltrates slowly, that could be a great concern on the surface, right? Because that might end up being flood conditions. If I have a soil that can infiltrate a lot, big pore spaces, but after a while, my water table can rise and rise and rise and rise. It can get more toward the surface. In other words, this water table can rise up to that surface, but if my water table reaches the surface, that means my ground cannot absorb all that water. And that also indicates I could have potential flooding conditions at the surface. That's why you may always hear about flash floods, because the soils cannot hold all that water that's coming down, especially if it's coming down way too fast. All right, this one here should be a time to climb. And if you want to, I'll put the link up there. You can work on some questions before you work on your homework assignment. All right, if you have any questions or concerns, you can see me for extra help on Tuesday. Thank you.